Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and in this video we are going to solve another gate question. This question is related to process management, to be specific to CPU scheduling, right? And this question was asked in the year 2017 for 2 marks. So let's read this question. So this question goes like this. Consider the following CPU processes with arrival times in milliseconds and length of CPU bursts in milliseconds as given below. Right? So what is this saying? That you have a bunch of processes P1, P2, P3 and P4, right? And their arrival time has been mentioned. So this is in milliseconds, right? And the length of CPU burst, basically the time that each process executes on the CPU, right? That is called burst time. The total duration during which the process is executing instructions is known as burst time, and that also has been given to you in this column. It is in milliseconds, right? Then what does it say? It says if the preemptive shortest remaining time first scheduling algorithm is used to schedule the processes, then the average waiting time across all processes is dash milliseconds, right? So the important thing to note in this question is that the scheduling algorithm that we are going to use to schedule these bunch of processes on the CPU is going to be preemptive shortest remaining time first, right? And after that, after doing the scheduling, what do you have to calculate? You have to calculate the average waiting time, right? So we have already talked about the shortest remaining time first in another video, right? So the basic idea, I'll quickly recall what do we do in shortest remaining time first before we go on to solve this question. So the basic idea in this scheduling policy, that is preemptive version of, so shortest remaining time first is preemptive, right? So the thing that we do here is that we prioritize that process which has the, as the name suggests, the shortest remaining burst time, right? It's very straightforward, right? If you have a bunch of process and you have to, if the scheduler has to make a choice, then the scheduler will pick that process which has the minimum shortest remaining time first. And this algorithm is preemptive in nature, which means that at any given point in time the scheduler has the ability to like take away the control of the CPU from the currently running process if there exists another candidate process which has a which is more optimal in the sense that it has a shorter remaining time, shorter remaining burst time, right? So this is preemptive in nature, and at any given point in time the scheduler has the full capability to preempt the CPU from the process, right? Or we generally say preempt the process from the CPU, whichever, right? So this is the brief idea behind the shortest remaining time first policy. So now, having understood this question, let's solve this, right? So this is the given data in the question. There are 4 processes. This is the arrival time and burst time in milliseconds. And the key points are that we are going to use shortest remaining time first. And what we have to calculate, it is average waiting time. It's a good idea that in the question, when you're solving any question, you keep in mind the important points, right? So now, in order to solve any scheduling question, right, most of the scheduling questions, you have to draw the Gantt chart and you have to perform the scheduling, right? So here, this is the Gantt chart that we are going to draw, right? And this says that we are going to use the shortest remaining time first, or SRTF algorithm, right? So let's start with process P1 because it is the first process that arrives in the system at time instant 0. It has a burst time of 7, right? So as you can see, process P1 has arrived, right? And this is t is equals to 0. At this point, we have not yet scheduled this process on the CPU. It has just arrived. Now, if you look at time instant t is equals to 0, there are no other process except P1. Other process, that is P2, P3, P4, will only arrive later, right? You can see P2 arrives at 3, P3 arrives at 5, and so on. So at t is equals to 0, since there is only one process, the choice is very simple, right? The only process that can run on the CPU is P1. There is no as such decision to be made, right? So P1 will be allowed to run on the CPU till when, right? This is the question. When you are solving any like similar question where you have to implement a preemptive algorithm, right? That is a there you have to keep in mind till what time instant will the scheduler allow this process to run on the CPU. So from time instant 0 till the time instant when another process does not arrive, until there is no other process, only then only until then process P1 will run. So in simple words, the next process arrives at time instant t is equals to 3, right? And so till t is equals to 3, from 0 to t is equals to 3, this process will run, that is p1 will execute on the CPU. And at t is equals to 3, when p2 arrives, then we have two processes in the system. From 0 to 3, right, there is only p1. So we are sure that this is the only process, so no other so there is no change to be made. But when process p2 arrives, then there are two processes in the system, and the scheduler has to again make a decision, right? Because it could be the case that p2 is a better candidate than p1, and then p1 will be preempted if it is indeed the case that p2 is a better candidate. So let's see which is the better candidate, P1 or P2. So since P1 has executed for 3 milliseconds, then the burst time reduces from 7 to 4. And P2 has a burst time of 3. So obviously P2 has a shorter remaining burst time, right? P1 has 4 and P2 has 3. So P2 is a better candidate as per the shortest remaining time first algorithm, right? So P2 will go next, right? And again we have to keep in mind how long. So P2 will execute until there is another new process in the system, right? Because till the time when there are only P1 and P2 in the system, we are sure that P2 is a better candidate. We just made a decision. But when another process comes into the, whenever a new process comes into the system, we have to re-evaluate, right? In case of preemptive policies. So the next process will arrive at t is equals to 5. So from t is equals to 3 till t is equals to 5, this process P2 will run, right? That is for 2 milliseconds. Its burst time reduces, remaining burst time reduces from 3 to 1, right? And at t is equals to 5, process P3 arrives in the system, right? So now again we have to make a choice. At t is equals to 5, there are three ready processes in the system, P1, P2 and P3. So let's see the burst times, the remaining burst times for each of these processes. So P3 has a burst time of 5, P2 has remaining 1, and P1 has 4. So obviously the best candidate, the optimal candidate as per the shortest remaining time first is P2, because it has only 1 milliseconds remaining and the other have 4 and 5. So we will allow P2 to execute for 1 more millisecond, and as you can see, it will then finish also, right? So at t is equals to 6, process P2 finishes, right? This is the completion time. And at t is equals to 6, the last process in the system arrives, that is P4. So now if you see, P2 has finished and there are three processes in the system, P1, P3 and P4, right? And at this point no new process will arrive, right? These are the only process that had to arrive, and all of them have arrived. So now the nature of preemptive shortest remaining time first kind of reduces to a shortest job first. Why is this the case? Because now whatever decision the scheduler will make, that is going to remain optimal, right? There will be no new processes arriving in the system, and there will be no further preemptions, because we now have a kind of global knowledge, right? These are the only process, P1, P3, P4 in the system. No new process will arrive, and this you can see kind of behaves like shortest job first, which is non-preemptive in nature, right? It is not the case that this algorithm is not preemptive. It is preemptive, but there is a special case that if all the processes have arrived, or if all the process arrive at t is equals to 0, then it reduces to shortest job first, which is non-preemptive. Because once you have a global knowledge, right, you can schedule it in the right order. So what I mean to say is that now you know that P4 is the one with the shortest remaining time, which is 2 milliseconds, and that is not going to change. No new information is going to come. So we can allow P4 to execute and it will finish. Then P1 can go, and then P3 can go. So what I did, you can see after all the processes have arrived, I just scheduled them in the increasing order of their burst time, right? So after all the processes have arrived, it becomes quite easy, right? Till the point the process keep arriving, then you have to be kind of cognizant that okay, a new process has arrived in the system and you have to re-evaluate. But after the point that all the processes have arrived, you just sort them in the increasing order of their burst times, remaining burst times, and schedule on the CPU, right? So you can see we have the Gantt chart ready. We have the completion times of all the process, and we can easily calculate the turnaround time, and from the turnaround time we'll calculate the waiting time. So what is the turnaround time? The turnaround time is the total time that a process spends in the system. It is calculated as completion time minus arrival time. So these are the completion times that we calculated, and these are the arrival times which were already given, right? And from this turnaround time we can calculate the waiting time, because This turnaround time, if you see, right, it is the total time that a process spends in the system, and this total duration is composed of two time fragments. One is the burst time, the time that the process spends executing on the CPU, executing instructions on the CPU, and the remaining time when the process is not executing, it is waiting for the CPU. So that is the part that makes up the waiting time. So by subtracting the burst time from the turnaround time, we can easily get the waiting time. So these are the waiting times for all the processes, right? So then we can take the average. So the average waiting time is 3 milliseconds. So that is the answer to this question, that is given this set of processes, arrival times and burst times. And if we use the preemptive shortest remaining time first, then the average waiting time for all of these processes is going to be 3 milliseconds, right? So guys, this is the solution to this problem. And this was it for this video. Thank you very much for watching. I'll see you in the next video. Thank you.